to the second installment of Unit 1, which deals with dimensional analysis. Going off of what we just talked about with significant figures, because of course, why do we use significant figures in chemistry? Well, because we're dealing with measurements, and there's some uncertainty in our measurements that we would take in the lab or that scientists might take performing research. When you are taking those measurements, there's really two different types of data that scientists can collect. Now, when we deal with measurements, that's called one type of data, and then more descriptive type of data is called something else. So descriptive data is normally referred to as qualitative data. If you are planning on going into psychology, it's very difficult to collect hard, solid numbers with psychological data. So normally that data is more descriptive in nature. And rather than calling that descriptive, we say that that is qualitative in nature. Scientists that obtain numerical data, on the other hand, that is known as quantitative data. And I always was able to differentiate the two because the word quantitative has an N in it. So quantitative data is always numerical in nature. So some examples of each of these. Qualitative data, like we said, is more descriptive, and usually these are found with observations. So you just look at something and you can figure out a qualitative piece of data about it. You don't have to write all of these down, but maybe you want to write down a couple of them. The solution is blue. You can look at something and determine that very easily. The sulfur smells like rotten eggs. Again, that's descriptive in nature. You're describing it, but you didn't need to take any measurements in order to figure that out. The hydrogen gas makes a loud pop when it's ignited. The base feels slippery. A solid precipitate is formed. All of those you can just see by looking at something or looking at a reaction. Whereas on the other hand, you can collect quantitative data through instruments, and a couple of different instruments that you might use would be graduated cylinders. You might have the scales or the balances, rulers, thermometers. You would collect numerical or quantitative data using those. Again, some examples. The solution has a volume of 45.2 milliliters. You would need to use a graduated cylinder in order to collect that measurement. And with that measurement, again, there's some uncertainty in that. Our graduated cylinders in class can't tell us 45.2063554 milliliters. Therefore, that measurement has three significant figures. There's some uncertainty in that because the measuring device isn't going to be that exact. The reaction was 90 degrees. Two significant figures in that value, measured on a thermometer, it's numerical. There are 24 students in the class. And just think about this, and hopefully I would have mentioned this in class by this point, but when you have a counting number, so you're counting 1, 2, 3, 4, 5, 6, 7, there's 24 students in the room. Is there any uncertainty in that? No, because there's exactly 24 students in the room. You can count that. That's a counting number. Because there's no uncertainty in that, that particular number has an infinite number of significant figures. I'm not going to have thumbs and fingers and toes and legs and drawers somewhere around the room, which means there's no uncertainty in that. So that particular number, 24, has an infinite number of significant figures. It's exact. It's not a measurement. It's a counting number. The length of the glass is 3.9 centimeters, also quantitative, as is the last one. The product of the reaction has a mass of 15.9 grams. In life, there are some very common units of measurement that you're very familiar with, and those are feet, yards, inches, miles, degrees Fahrenheit, gallons, and pounds. However, sorry, in chemistry class, we don't use these types of measurements. For some reason, Americans use all of these funky units of measurement, which really goes against what the rest of the world does. And in order to be consistent and to compare data from scientists in the United States versus scientists in other parts of the world, we use a common system of measurement, and that measurement is the International System of Units, or the SI system, and this is basically your modern day metric system. In chemistry, we are going to use basically 6 of the base units using the metric system, and let's just go over what those are. So your base unit for length is the meter, and a meter is about a yard. I don't remember. I think a meter is a little bit longer than a yard, but don't quote me on that. I always forget which one's a little bit larger, but it's about the same length. And a meter has a symbol of a lowercase m. Mass, the base unit is the gram. Something that's about 1 gram would be like a paperclip or something like that. And we can add prefixes to that to make those units either bigger or smaller, which we'll talk about in a second. Grams has a symbol of a lowercase g. Volume is the liter. Liter is kind of similar to like a quart. Uppercase L, or a capital L. The reason why it's capital is because if you do a lowercase l, it looks kind of like a 1. So to differentiate between the two, we always do a capital letter L. Amount of a substance is the mole. Not something we're going to work with just yet, but just so you know, that is the base unit, and the mole is represented by MOL. Notice it's not just an M. We like to differentiate between those different units. So the meter is the M, the mole is MOL. Why didn't they just tack the E on there to finish the word? I don't know, but that's the symbol. Energy is the joule, which is a capital letter J, and time is the second. So those are going to be the 6 ones that you encounter the most. There's some other ones that you might see, like a Pascal as a unit of pressure. Don't worry about those as much. But like I said, we can add prefixes to those base units in order to make them larger or smaller. So this right here, this paper, you hopefully have the paper with you at this point, but or it is in your notes. I did put it there. But this represents everything with the meter. Now, this works not just for meters, but it works for any base unit. So wherever it says meter on this, you can replace with liter, you can replace with mole or second. It doesn't matter. All that matters is those examples on the end. So, or the ratio of the base unit to whatever the prefix is that you're using. You will see the names of the prefixes over on the left here, and you'll also see those abbreviations, which is really important for you to recognize. So like a centimeter, you would put a lowercase c in front of the symbol for meter, which is a lowercase m. For a kilometer, you would put a lowercase k in front of the m. A megameter would be a capital letter M, which is different from the lowercase letter m, which is different from the micro, which is a this mu symbol right here. It's like a U with a little tail in the front of that. What I generally like to look at when I'm doing dimensional analysis is this example part right here. So if I were you, I would take a highlighter or something, or your pen, and just circle this, because this is really, really, really important, and what I'm going to be referencing as we start doing dimensional analysis problems. But these SI prefixes, again, works with all of those base units here. So wherever you see the meter, this also works for grams. So like 1 decagram is equal to 10 grams. And that makes it really nice, because that's why the metric system is so great, is because it's very, very easy to follow and everything works all in the same ratio. I just talked about dimensional analysis, but what is it? Well, dimensional analysis is a mathematical technique that's used to convert between different units to solve problems involving measurements. So sometimes you might be given the units of, or the measurement of something in one unit, and you don't need it in that unit. You need it in a different unit in order to perform a calculation. So dimensional analysis is the technique to convert one unit into the other, using these right here usually. Or there's the the other side of the paper, which has some of the other conversions on it. So you might also need to know that like there's 12 inches in a foot. You can also use those conversions as well. I always think it's much easier to actually do a dimensional analysis than it is to talk about how to do dimensional analysis. So we're going to dive in and do sample problem 4 together. So sample problem 4. Sample problem 4 is asking us to express a mass of 5.712 milligrams in units of grams. Let's just double check. Yes, grams to milligrams. So that's what we want to find. The way we want to set these problems up is, of course, you always want to start off with whatever the problem wants you to convert. In this case, it's the 5.712 grams. Always write your units down. I can't stress this enough. So this right here, you really need to include the units of grams. If you don't, and when the problems start to get a little bit more complex, it's going to be very difficult to keep your work in order. And in chemistry, we always want to keep the work as neat and orderly as possible. The way I solve these is putting a little crosshair with the number that we want to convert in the upper left-hand corner. When we're converting, technically any number is over 1. So I like to put a 1 there, and that 1 just acts as a placeholder. That's what that 1 is right there. So I just like to put that there. It really doesn't make a difference when you're solving the problem, but sometimes I think it helps students kind of visualize what we're doing. And whatever unit we want to convert out of, whatever's on the upper left-hand corner, I have to bring across and below. So notice here, units of grams are opposite one another. That's very, very important. The unit that I want to convert to is going to go on the top. The reason why is because mathematically, these units of grams and those units of grams will cancel out because you're dividing them by one another. Notice I didn't even plug any numbers in yet because I always stress to my students, you need to have your units in order first. The work is not going to work out very well if you don't have the units set up just perfectly. So what I'm going to do now is to go back and look at that SI prefixes, the one that I told you to circle or to highlight. So whatever you did, I need you to reference that. And I want you to go down to where it has the prefix for milli. And I'm just going to write down exactly what it says on that particular part. On that chart, it says that 1 millimeter is equal to 0.001 meters. So I just copied that down from that chart. And that's very important. This is what we call a conversion factor. This is what's going to allow us to convert from one unit to the other. However, that really doesn't help us so much in this particular problem. It does, but we don't plug it in this particular way. So another way to represent a conversion factor is by a fraction of sorts. And we could do that by writing 1 millimeter is equal to 0.001 meters. Or we could flip that and basically say the same exact thing. 0.001 meters is equivalent to 1 millimeter. So all of these three things mean exactly the same thing. Okay, these are all different conversion factors of the same equity. They all mean the same exact thing. Something I should have done before I started going into this was, even though that paper has all of these listed in units of meters, remember, this is good for any base unit. So I'm just going to take my white out here and just white these out. because really anywhere you have that meter, you could substitute for the gram. So 1 milligram is equal to 0.001 grams. That's the same exact thing. Also the same as that. And let's do this last one here. 0.001 gram is equal to 1 milligram. So all of these mean the same thing right here. What we have to do is find out which one of these two in particular, works to cancel out the units of grams. So if I have 1 milligram on top and 0.001 grams, see how the units match up with this right here? This is how I'm going to set up my problem. 1 milligram is going to go on top, and that's equal to 0.001 gram. In this case, see how the units don't work out? Here I have 0.001 grams on top. If I were to plug that in, look, grams and milligrams, that's not opposite one another. This is not going to work out. We're going to get the wrong answer if I try to solve this. So we had to use this particular conversion factor. Again, these three all mean the same exact thing, but they're different ways of representing them. This right here is my equity, my conversion factor. Units are in the right place. The way we would solve this is you want to multiply straight across. So 5.712 times 1 is 5.712 over, and again, multiply straight across. 1 times 0.001 gives me 0.001. And then you're going to divide for the very last step. 5,712, that's a comma. Do not forget the units. Units are super, super important. So whatever unit you're left with on top that's not crossed out, that's going to be the unit for your final answer. Milligrams. Now that was a lot of work for one problem. You do not have to do all of this work. You really don't have to write this out, though sometimes it helps. You don't have to write that out, but sometimes it helps. I'm just kind of showing you very explicit instructions on how to do this to start. Let's try sample problem B. So B says express a mass of 5.712 grams to units of kilograms. So we're still going from a base unit to a unit that has a prefix in front. However, we're going to a larger unit instead. Kilograms are going to be larger than grams. You know that because towards the top of that paper or of that chart, those are your larger units, whereas the bottom is going to be very, very small units. So let's set this up like I did before. 5.712 grams. Set up my little crosshair. I'll put a 1 below as a placeholder, just like I did up there. Whatever unit it's up top, I have to bring down. I didn't plug any numbers in. That's important. Put the units in first. I really can't stress that enough, because now these units of grams will cancel out, and your answer will be in units of kilograms, which is what the question is asking. Let's find the equity between grams to kilograms. So if you look on that SI prefixes chart over on the left-hand side, or the right-hand side, I'm sorry, towards the top, you'll see that it says 1 kilometer is equal to 1,000 meters. Remember, you could just replace the meters with any of the base units. So I'm going to replace meter with gram. So this tells us that 1 kilogram is equal to 1,000 grams. That's my conversion factor. It's telling me the relationship between kilograms to grams. Like I said, this doesn't technically work in here, that you could figure out where the numbers go by looking at that. Another way to represent conversion factors, like we said, is using the ratios. So let's just write it this way. 1 kilogram over 1,000 grams. Or we can represent it as 1,000 grams over 1 kilogram. All the same way to represent, or different ways to represent the same thing. Let's figure out which number has to go on the top. So, if I use this one first, notice how I have grams up top and kilograms on the bottom. Units are not going to cancel out. This is going to give you the incorrect answer. Therefore, you need to use the one that has the 1,000 on the bottom, because if you look at the conversion factor, 1 kilogram is equal to 1,000 grams. 1 kilogram is equal to 1,000 grams. I always tell students this is not a memorization thing. Don't memorize, oh, 1 goes on the top here and 1,000 goes on the top here. No memorizing. Chemistry is not really a memorization topic, unlike other topics that you're used to. You really need to understand the process for this. So 1 kilogram is equal to 1,000 grams. It just happens to be by chance that both of these problems have the 1 on top. You're not always going to find that. And to solve, multiply straight across. 5.712 times 1 is 5.712, divided by 1 times 1,000. And then divide. You should get 0.005712. And don't forget your units. Whatever's left up on top that's not canceled out, that's your unit or your final answer. We should keep significant figures here too. Now, some of you might be thinking, wait a minute, this only has one significant figure. This is not a measurement. These numbers here have an infinite number of sig figs. You don't measure that. That's a fact. We know that. There are exactly 1,000 grams in 1 kilogram. Let's try C. C is asking, express a volume of 1.2 liters to units of centiliters. I would recommend trying this one first and then kind of watching to see how I solve it. So if you want to pause this video, try this one and then watch the answer. Start it off just like I did, 1.2 liters. Let's put the 1 as a placeholder down below. Whatever units up top, I'm going to bring down. And we'll bring centiliters on top, because mathematically, these units will now cancel, which is what we want. They always have to be opposite one another. Look on your chart. That chart tells us that, let me get this screen out of the way so I could see, so I have it right. This is a centimeter again, but remember we could always replace the base unit. So 1 centiliter is equal to 0.01 liters. I'm not going to make those fractions here because I think you could see kind of where I was going with that, but we need to make sure we represent these the correct way. Notice there's a 1 next to centiliter. So 1 centiliter is going to go on top, is equal to 0.001 or 0.01 liters. That's going to go on the bottom. Again, it's a coincidence that all of these have a 1 on top. It's not always going to be the case, so please make sure you're following the steps as I'm showing you. Multiply straight across. 1.2 times 1, of course, is 1.2. 1 times 0.01 is 0.01. Final answer is 120. Don't forget your units. Whatever's up top becomes the unit for your answer. And there's that. Answer should have 2 significant figures. So that has 2. This is infinite because that's exact. That's not a measurement. That's a fact. This should also have 2 significant figures. Let's try D. So D is a problem that is not in the metric system. So let's go ahead and do this one. So D says express a length of 148.29 inches to feet. Not the metric system, so you don't even have to look at that paper or that chart. We're always going to start off with what I want to convert. 148.29 inches. One below is a placeholder. Don't put any numbers in. Inches. They have to be opposite. And I could convert to feet. Let's cross out the units of inches. It's always a good thing to do is to take the things that you know how to do first. Just get all that out of the way. Students usually like to they rush. They go so fast through these, and they're like, I want to get the wrong answer. Well, because you're rushed. Just do what I show you to do, and you should not get the wrong answer. So, on the back of that paper that I gave to you, the one that has the other conversions on it, well, you should really know this one anyway, but there are 12 inches in 1 foot. We know that. And this has an infinite number of significant figures because that's not a measurement. We know that for a fact. We have to figure out where to put these numbers. Again, we could do 12 inches in 1 foot, or we have to represent it this way. Which one of those best fits into this dimensional analysis problem? Well, 1 foot needs to go on top because if I do it this way with 12 inches on top, our units aren't going to work themselves out. 1 foot is equivalent to 12 inches. Again, it's coincidence that all of these have a 1 on top. I really need to change that in the future, but I don't think it's going to happen anytime soon, especially since I'm making this video. Multiply straight across. 148.29 times a 1 is 148.29. Divided by 1 times 12 is 12. So let's go ahead and perform this calculation. 148.29 divided by 12 gives me this answer. I'm going to write the whole number down. 12.3575. But remember sig figs, so now you know how to round your final answer. This first number is a measurement. So this has 5 significant figures. This 12 on the bottom comes from the 12 inches. Now that is not a measurement. That's an exact value. So that is infinite number of significant figures. Therefore, your final answer needs to have 5 sig figs. Right now this has 6. Let's round it to 5. 12.358. And don't forget your units. Let's find my green pen here. Units would be whatever is left over, which is the foot. Again, you don't have to do all of that work, but I'm just kind of showing you very in-depth for right now. Let's try E. This is an interesting one because unless you know the conversion from minutes to years in one step, which I don't know, but if you're into the theater, you might know that song, and you're probably singing the song to yourself right now. I don't know how many minutes are in a year. So in this case, we need to do these in multiple steps. Express a time of 0.05 years to units of minutes. So we got to take this one step at a time. Let's start off with what we have, years. 1 down below is a placeholder. Bring year down, and let's convert to something that's smaller than a year, but not as small as a minute. It's something that we know of. Now, you can convert it to months, but when you go down lower than that, there are not an equal number of days in every month. So I would recommend converting years to days. Because we know that 1 year has 365, if you want to be really precise, 0.25 days. That would have 3 sig figs because that's not an exact value. This is probably also not exact. The reason why we have a leap year is because there's not exactly 365 days in a year. It's about 365 and a quarter. So 1 year is equal to 365.25 days. These units cancel. What you can do is you can now solve this and get units of days and then convert days to whatever unit you want. I don't like to do it that way though, because I like to just make one longer problem. Though you could technically solve this and get the same exact answer. If you'd rather do this in one-step problems, do that. And as long as you get the same answer that I get at the very end, then you should be great. Let's start off just like we did before. We're going to bring units of days because this is what unit my answer would tell me. Let's bring days down and convert to something that's closer to a minute. Now, I don't know how many minutes are in a day, but I do know how many hours are in a day. And we know 1 day has 24 hours. A lot of times what students will do is they won't really think about what they're doing and they'll say that there's 1 hour and 24 days. They'll switch those numbers. You have to make sure you put the number next to the correct unit. So now those units of days will cancel. Look, because they're opposite one another, days and days. We're not done. We're not in the correct unit of minutes. So let's convert hours, and I do know how many minutes are in an hour, because 1 hour has 60 minutes. How many sig figs are in both of those values? Infinite. It's not a measurement. That's exact. If you use a stopwatch, there's exactly 60 minutes in an hour, or 60 seconds in a minute, however you wanted to think about that. Let's go ahead and get this color here. Units of hours now canceled. Notice I didn't even pick up my calculator yet. Didn't even pick it up. So let's go ahead and solve for this. Multiply straight across, which actually is all of the numbers multiplied by one another. 0.05 times 365.25 times 24 times 60 gives me this answer right here. 26,298, which would be over 1 because everything is 1 on the bottom, which would be equal to 26,298. Units would be minutes. However, how many sig figs do we need in our answer? Well, I hope you can't hear it. How many significant figures does this answer need? Well, this has infinite, that has infinite, so it's not that. We said before this has 4 significant figures, but the initial measurement that I've given has only 1 significant figure. So how do I make this answer have only 1 significant figure? It's a big round. It's a very big round, but the reason why we can round it so much is because this initial measurement really isn't that exact. Therefore, we would want to round 26,298 to have 1 significant figure, which would mean my final answer is 30,000 minutes. Again, yes, it's a big round. Yes, it's a weird concept, but because we can't be that certain about this measurement to begin with, we can't be this certain about this number. So we have to take that into consideration. Again, if you were to do this with every individual step, so if I were to do this, break this down. So I'll just do one here for you quick. If we had 0.005 years, and converted years to days. 1 year has 365.25 days. If we were to solve for that, 0.05 times 365.5, I would get about 18.275 days. If you would rather do this in one-step problems, you would take this answer, plug it into a new conversion, 18.275 days, then convert days to hours. And we know one day has 24 hours. So again, let's do that work quick. We get 438.6 hours. Now, we still want to know what this is in minutes. So let's convert 438.6 hours to minutes. 1 hour has 60 minutes. So times 60. Boom. Not the exact same answer, but pretty darn close. The reason why you're not going to get exact is because of rounding throughout. 26316 minutes. But look how darn close those two numbers are to one another. No matter which way you do it, you should get the right answer. Do whatever way you are more comfortable with. And that's either doing it in one long problem like I showed you before, or you could break it down into 3 one-step problems. Some students like doing it this way, and that's fine. And some students like doing it this way, and that's fine. It's really up to you. I know with some of these first ones, I could just move the decimal and let me just do that. Well, you can, yes, but a lot of times students move it in the wrong direction, which goes against what we were doing over here. This skill in itself, dimensional analysis alone, is very important in chemistry. It's not just converting units of length or volume to one another, but you do have to know how to convert units like moles to grams, which we're going to talk about, and atoms to moles, and units of pascals to units of atmospheres. That's really, really crucial as we get more into chemistry. So it's not always going to be just moving the decimal point. You do have to know this overall process. If you have any questions on this and any of those 5 problems, please make a note and ask me a question next time you see me. I'll give you a chance to ask any questions that you may have had. Otherwise, we're going to do a lot more practice with this in class. And I will see you in the next video. Bye.